there's an online system about hundreds of people watching.
I see.
So what happens here is that we have WeChat group, WeChat group with about how many? I think 2,500 in total, but not all of them actually attend. But usually hundreds. Then they will they'll ask questions. Then I can see them. I can translate those for you.
Ah, I see. Because they might not be in English, the questions.
Yeah.
I see. All right.
Yeah.
Great. Thank you.
Yeah.
So how are you doing?
Good.
Yeah. So it's very early for you, no? What time is like 7?
7.
Yeah.
Now I'm a morning guy, so I
I see.
slept about 7 hours. It's good, right? So here, after this seminar, I go to the Chinatown to get some breakfast.
Okay. Cool.
Yeah. So, but do you have introduction slides for your group and everything at the very beginning?
Yeah, I have a few because you suggested I add something. It's pretty brief, so I don't know how much detail. Basically, I just give an overview.
This is a good opportunity for like people seeing your work and because sometimes I read papers like but seeing this is actually good when people may contact you. Then this is what how because most of the students here are actually graduate students, and all the graphics faculties in China, including.
Oh, right. Okay.
Certainly we have senior fellows. If they have time, they actually listen to the talk. So last time we had like a few questions, right, from Zhejiang University, not the students and the senior students. So I think Amir, the guy who chaired the SGP 2 years ago, so he gave one, I think early this year.
Okay.
So I gave one early this year. He gave one. So there'll be more your speakers from European and so we have a committee. So I'm Jun Yang, the Cyclogun guy. So we are responsible for this international connections, and then within each direction we have two senior guys in charge of the program.
I see.
So, yeah.
Okay, great. Oh, and just very briefly before we start, you know my postdoc Ruchi Huang?
Yeah.
He mentioned he asked you for some code. I don't know if you have time. I mean, I'm sure it's super busy.
Yeah, I'll send it. Yeah,
if you have a chance, whenever you have.
Yeah.
There's no hurry, but I think I think he's trying to submit something for your graphics. So if,
Okay.
we have a bit tight deadline.
Yeah.
Okay, great. And then will you do some introduction before, or shall I introduce myself?
Yeah. So once the seminar starts, I will do the introduction.
I see. Okay, great. So then I also have a couple of slides about myself, but I can go.
I will say something different.
pretty.
Yeah.
I see. Okay, great. So are you going to ICCV? I guess you probably are. Yeah.
Yeah.
You switched a bit from graphics, right? Yeah. So, I think so. Yeah. I see you have lots of papers and yeah, exactly.
Yeah, it's huge now. Yeah, huge.
Yeah, and I guess most students are 1,000. Yeah. Yeah, I think it's somehow doubled from last time. So in 2 years, it doubled it. Yeah, it's really crazy. Yeah, where are all these papers coming from?
So right now, I think the senior guys most go to the workshops.
Right.
Yeah.
Because it's a bit more manageable. Yeah. And what happened to your student who was interested in topology? Is she still working on something?
Well, so let's talk about that later.
Okay, sure. Okay.
Yeah.
Okay. All right. So Jesse, let me know when you want to start.
Okay, maybe you can start.
Yeah, I have started.
Okay.
Okay, shall we start?
Yeah, for me it's okay. I don't know. I don't hear anything.
Yes.
Okay, so good evening, everyone. So it's 8 p.m. in China. So we are very honored to have Max Ovsyannikov to give us invite the talk some recent methods in non-vegetation measuring with and without learning. So I know Max for many time, more than 10 years. So we graduated from that same episode. He's right now a professor in Polytechnic in France. So he received his PhD from Stanford with excellence in research award from the Institute for Computational Mathematics and Engineering. So he's a recipient of many awards. Okay, he's a recipient of the UGRAF Young Research Award. He has ERC starting grant, and he has many best paper awards. So his most well-known works includes heat control signatures, functional maps, intrinsic symmetry detection, and many, just to name a few. Okay. We are very happy to have Max to give a talk today. And Max, you may start.
Okay, thank you very much. So thank you, Xing, for the introduction, and thank you for having me. So this is the first time for me to give this kind of a webinar, so I hope it goes well. It's a bit strange, not to see the audience in front of you, but I think it should be okay. So thank you, everyone who can connect. And this is I'll basically give an overview of some of the work that we've been doing in the past few years. And this is joint work with many different people, and I'll be naming some papers as I go along. But the overall theme is basically we're trying to develop methods for shape matching and shape correspondence. So before I start on the technical part, I just want to give a little bit of background about myself and our group. So as Xing mentioned, we did our PhD in the same group, advised by Leo Gibas at Stanford. And then for a year I worked at Google, and since 2012 I'm a professor in the computer science department at École Polytechnique in France. So just as Stanford is a bit of in the outskirts of San Francisco, École Polytechnique is basically in the suburbs of Paris. So just for those who maybe don't have too much information about École Polytechnique, I want to give a brief overview. So this is a small school, relatively small, especially by Chinese standards. I'm sure it's very small. It's about 3,000 students, and it's located very close to Paris, the capital of France, and it's kind of difficult to compare to other big universities, but it was ranked the second best small university in the world in 2019 after Caltech. And it has a very rich history, especially in technical sciences and in math. So there are very many famous professors and students who studied and taught at École Polytechnique, especially French, like Ampère, Poisson, Poincaré, and Fourier, to name a few. And what I wanted to mention especially is that nowadays, even though it's kind of well known in France, the campus is very international. So we have many students from different countries, including from China, and there are quite a few connections with universities in the world. And just about our group, basically I'm currently supervising 5 PhD students and 2 postdocs. And I'm also part of a larger team, which includes myself and 3 other professors. So some of you maybe know Marie Polkani. She was the paper chair for SIGGRAPH a couple of years ago. So she's part of the same team. And we have many international collaborations with universities in the US, Europe. Don't have so many collaborations with Chinese universities, but maybe that will change. So maybe this is a good opportunity also to meet some people right now. And I wanted to mention that we have plenty of funding for both PhD students and postdocs. So as Xing mentioned, I have this ERC starting grant, and it's really meant to basically attract top talent from all over the world. So it's not an issue if you have a nationality of any country. So we always try to accommodate for that. So please let me know. If you're interested in working together, just drop me an email. I'll be happy to, to discuss different possibilities. All right, so this is some background about ourselves. So as basically I was thinking about what to talk in this webinar, and I wanted to basically give a high-level overview of some of the techniques we just been working on and kind of we've been studying. And there's a general theme of basically trying to create tools for computing and analyzing mappings between geometric objects. So geometric objects are, at least for the purpose of my talk, are shapes that can be represented as point clouds or triangle meshes or maybe volumetric data, especially if you're working in medical imaging, or maybe even images. And the general theme is basically, we want to create techniques that are somehow agnostic to the underlying data representation and maybe can be applied universally. At least this is the ultimate hope. I think we're not quite there yet, but this is what we're trying to do. And basically my talk will be based on a series of works, and the foundation for this work is based on this paper that we published in 2012, and then since then we've developed a lot on this functional map representation for correspondences. And just to kind of give maybe some advertisement, so we did a course at SIGGRAPH in 2017, and if you're interested in some of this material, there's we prepared a set of course notes that kind of describe all of the things most of the things I'll be talking about in more detail, and also we provide some sample code on this website that you can go to, download, and play with and see maybe it could be useful in some of the problems that you're working on. So this is kind of the foundation, but I'll talk about various things. So I'll kind of first describe what is the problem that we're trying to study and maybe give a kind of a classification of different instances of this problem. Then I'll describe a very classical algorithm for solving a particular instance of this rigid alignment problem, which is called iterative closest point, which probably many of you know. But just in case some of you don't, I think it's like one of the most essential algorithms in geometric data analysis, so it's good to give an overview. And then I'll talk primarily about this functional map representation and list some of its properties. And like I said, this is kind of the essence of many of the things that have followed since 2012, so I dedicate a bit more time to this particular part and describe kind of the basic pipeline for computing correspondences using this representation. And then in the end, I'll talk about a couple of extensions, more recent extensions, and some improvements to this pipeline. And in particular, in this last part, or maybe the second half of my talk, I'll basically talk about two recent works, one that is just accepted to ICCV and another that just was accepted to SIGGRAPH Asia, both in 2019. So this is the sort of the recent part of my talk. And at the end, I'll mention some open problems, if you have any questions. Okay, so basically, what is the context for all this work? So primarily, my background is in geometric data analysis, which maybe subpart of it is called geometry processing, right? And it's all about representing and manipulating shapes. And so just to kind of make something more precise, what do we consider a shape in this domain in geometry processing? Essentially, we kind of have this dual view of the world. We think of shapes as both discrete objects that are given on a computer, and typically these are represented as a set of points and a set of triangles connecting them. So this is what's called a triangle mesh. So here is an example of such a representation. And at the same time, we think of some kind of underlying continuous structure that we typically don't have access to. And this continuous structure is often thought of as a surface embedded in 3D. So in this case, you might think, for example, you have this discrete object that somehow samples this continuous surface, and maybe it's a sphere, or maybe it's some kind of a polyhedron like this. But the reason why we typically think of a surface is because then we can use tools from differential geometry to both inspire some of the techniques that we develop and also prove some properties. And often what we would like is, have some kind of a construction that makes sense in a discrete setting that we can, compute on a computer, but also ideally makes sense in a continuous setting so that if you, for example, refine your mesh, so you add more and more points or samples on the surface, then in the limit you converge to something that kind of makes sense. And the typical assumptions, at least for this talk, is that the surfaces that we're dealing with are connected, manifold, and without boundary. Although most of these assumptions can be lifted in practice, you just have to be a little bit more careful of how you deal with the data. But just to simplify things, we assume that we're typically dealing with connected surfaces without boundary. So there are many different kinds of sources of this type of data. So some of you maybe are familiar with shapes that appear in commonly used benchmarks. So there are these very famous benchmarks now that contain, hundreds or even thousands of shapes. So common benchmarks that we use are from MPI Faust, Scape, and Tosca. These are very classical data sets that contain shapes represented as triangle meshes, and these are often characters that maybe appear in games or special effects. And what's important here is that the complexity of these shapes can be quite high. So for example, if you're dealing with a single object, you might be dealing with either, somewhere in the range of 5,000 to 200,000 or even more. Nowadays, you can have objects that are maybe millions of triangles. So what that means is basically that the algorithms that we develop should be efficient enough to accommodate this kind of complexity. So if you have a method that's maybe quadratic in complexity, this is already too slow in many settings. So the overall goal, at least for the first part, but I mean, a lot of my research is driven by this problem of basically given a pair of shapes, how do we find correspondences between them? So what are correspondences? These are basically like some connection. So, for this tip of the ear of the armadillo on the left, somehow we want to find the corresponding point on the tip of the ear of the armadillo on the right. And this is a kind of a problem that is very easy for us to do, or relatively easy for us to do as humans, but it's very difficult to construct an algorithm that would be able to do this efficiently. And it's a problem that kind of combines two aspects. There is the geometric aspect, which is, like good correspondences. For example, we know they should be continuous, or they should maybe preserve distances or something like that. But it also has a semantic aspect, which is, this point should go here because these are knees or something. And this is actually very difficult to encode in a purely axiomatic way. So towards the end, I'll talk about learning-based techniques to address this problem. And so, this problem is finding correspondences is also called finding the best map, or non-rigid alignment is basically variants of the same problem. So there are many different instances of this problem. So to just kind of make things a bit more clear, I listed some of the categories of this shape correspondence or shape matching problem that might appear. So one big distinction is whether we're dealing with a local or global alignment. So local means that you start with a pair of shapes that's already approximately pre-aligned, and global means basically you have two shapes that are at arbitrary positions, so there's no assumption on how they're oriented in space. Another big distinction is rigid versus deformable. So rigid means we only allow, let's say, rotation and translation for the shapes, and deformable means that there's some general non-rigid articulated or just general deformation that is accepted and we don't know what it is in advance. Another big thing which is especially important in practice is what I call semi versus fully automatic. And semi-automatic basically means you ask the user sometimes to give a few landmark correspondences, and then the algorithm tries to extend those landmarks to all other points on the shape. And this, is acceptable in some settings, but ideally we'd like to avoid. So, fully automatic is basically you have some a priori model that you try to find correspondences using that instead of landmarks. And then finally, especially recently, there is a lot of work on learning-based techniques, and I'll talk about some of those towards the end, versus, purely direct data. So today I'll primarily be talking about these categories, so global, deformable, automatic shape correspondence with and without learning. This is a very difficult problem, and there's lots and lots of work that's been done to address this problem. Of course, we're not the first ones. So, why would you be interested in this? I mean, what's the use of these shape correspondences? So you can imagine that once you have a shape correspondence, you can do many, many things with it. So one kind of important theme in all of these is that you can transfer information. So for example, you can transfer texture or parameterization, you can transfer segmentation and labels, or for example, you can transfer deformation. So this is especially important in animation, where it's very time consuming to create detailed animations of complex shapes, and you need to hire highly skilled professional animators. But once you have a correspondence and an animation defined on one shape, you can try to transfer it to another. And there are many other applications like statistical shape analysis or shape interpolation, reconstruction, but they all have this kind of general theme of transferring information across a pair of shapes or maybe a collection of shapes. So just to maybe give an overview of the simplest version of the problem, which some of you are familiar probably with, is rigid shape matching. So rigid shape matching is we're given a pair of shapes. So here they're in gray and in blue, and we'd like to find the optimal rigid alignment between these two shapes. So what that means is we'd like to find some rotation matrix R and translation vector T, such that after we apply this rotation and translation, the two shapes in some sense align to each other. And this was a problem that was especially prominent in shape reconstruction in the late 90s, early 2000s. So there's a very classical algorithm to solve this problem, which is called iterative closest point. And basically it's based on the following two steps. So we have a pair of shapes, M and N, and in this case, what I'm showing is basically an example in 2D. And it iterates in two steps. So first, for every point xi on M, so for every point on the red curve, we find its nearest neighbor yi on the blue curve, right? So here, for example, for this point, the nearest neighbor is here. For this point, the nearest neighbor is here. And then, once we find these nearest neighbors, we find the optimal transformation, R and T, that would minimize the distance between the transformed original point, so the xi after the transformation, and its corresponding point yi, right? And so our goal is to find this R and T, so this rotation matrix and translation vector, that would minimize this sum of the distances. And so once we do that, we apply this transformation to all the points, and now we see that, okay, we didn't fully align the two shapes, but somehow they came closer. So we basically repeat this procedure. So once again, we find the nearest neighbors, yi, for every point xi, and then we find the optimal transformation, and then eventually we converge to the global optimum. So this algorithm is very simple and very efficient, and the reason why it's efficient is essentially because this problem solving, so both finding the nearest neighbors and finding the optimal transformation, rigid transformation, can be done very quickly. So nearest neighbor search can be done, for example, with efficient space partitioning, like with the KD trees, and then the optimal transformation can be done explicitly. Basically, there's a closed form expression that you can compute using singular value decomposition of a covariance matrix, basically. So both of these steps are very efficient and can be done, with hundreds of thousands of points, and we can show that under certain conditions this algorithm converges to a global optimum if you start near the optimal alignment. So this is kind of very nice, but what we're interested in is non-rigid shape matching. And the problem is, basically, in the rigid shape matching case, we had this very nice parameterization of the variables, of the unknowns. So we're looking for rotation and translation, but when you're considering the general problem of non-rigid correspondence, for every point x, the space of basically unknowns is all the other points t of x, so the image of x on the other surface. And so there's no this compact representation for the correspondences, which makes the optimization extremely difficult. So the two main questions in this domain are, and I would say that they're still not solved, but this is kind of very useful to think about in general. So first of all, what do we mean when we say that a correspondence is good, right? Because non-rigid basically means arbitrary, right? I mean, you can assign any point to any other point. So you need to kind of construct a notion of good correspondences. And the second is more algorithmic, is how do we compute these kinds of correspondences efficiently in practice, right? So one very useful deformation model, even though nowadays I would say it's not used as much, but at least is good to think about and good to keep in mind, is what's called isometric shape matching model. And this model is trying to answer this question of what does it mean to have a good correspondence, and essentially it looks at the following. So suppose that I have this shape M, right, and I have this other shape N. Then I look for a mapping T, right, so a mapping between the points on these two shapes, such that the geodesic distances, so the geodesic distance is basically the length of the shortest path between a pair of points on M, X and Y, but the shortest path has to lie fully on M, right, so we are not allowed to make shortcuts in space, so that's what's called a geodesic. And ideally we'd like to find a mapping such that the distances between pairs of points X and Y are the same as the geodesic distance between images of X, so T of X and T of Y. And you can write this compactly like this, saying, so basically for every pair of points X and Y on M, we would like to have the difference between the geodesic distance on M should be as small as possible to the distance, or as close as possible to the distance between the images of X and the images of the images of X and Y on N, right? So the geodesic distance between T of X and T of Y should be the same as the geodesic distance between X and Y. So this is nice, and why is it nice? Is because especially it allows us to find approximately non-rigid correspondences that correspond, for example, to articulated motion of humans. So, if I'm standing up straight and then I raise my hands, the Euclidean distances, so the distances between points in space, might change, but the geodesic distances should be approximately preserved. So this is where this model is coming from. So this is a nice notion of what kinds of correspondences we're interested in, but the problem is computationally it's very, very difficult to solve. So in full generality, this is close to a graph isomorphism problem, which is even on graphs is very tough. So basically the main problem is that the space of possible solutions, so the space of unknowns, so in our case this space of unknowns is this T, the mapping T, becomes not only large because for every point on M we can find basically any point on N, this is the unknown, so these are the variables, but also it's nonlinear and non-convex because basically the image of any point X can be any other point Y, so this is any other point on N, so this is a point that lies on the surface, so it's non-convex, nonlinear space. So basically, people tried to use this, but this led to very difficult optimization problems. So in order to kind of address this, we propose a different representation, which is called a functional map representation. And in the first part, I just want to give an overview of this representation and its main properties. And basically, it allows us to encode correspondences between shapes as small size matrices that then we can manipulate and optimize for efficiently. And what is nice is basically the size of these matrices doesn't depend too much on the number of vertices on the shape. So this makes the optimization very efficient. It also allows us to do certain things like, for example, handle uncertainty or ambiguity. Like in some cases you say, okay, at this point, I don't know if we should go here or here. If you have a point-to-point map, this is difficult to encode, but with a functional map representation, it's easy. And also you can do certain things like compose maps or average them using basic linear algebraic tools. And what's especially important for the problem that I mentioned is that the optimization problems that we need to solve in the end turn out to be very simple convex optimization problems. So the essence of this representation starts with the following. So we start with this pair of shapes M and N, and let's suppose that somebody gives us a map, so T. This T is a point-to-point map that takes points on N and produces points on M. So here for convenience, I reverse the order of the map, so it used to be from M to N, now it's in the opposite direction for a reason that will become clear in a second. And like I said, once you have a map, you can do many things and you can transfer information using it. And what is the simplest thing that you can transfer? Probably the simplest notion is transferring real valued functions. So suppose that I have so how would this work? Suppose that I have some real valued function, so f, that basically takes values. So basically for every point on M, I associate some value in the real. So you can think, for example, like temperature. So every point on M has some temperature value. And this is my function f. And then I can use my initial correspondence t to transfer this function f to another function, but now that is defined on n. And how do I do this? Simply by composition. So for every point on n, I just look at its image on M. I look at what is the value of f on this image, and then I just borrow that value. So compactly, you can write that there is some kind of a functional transformation that takes functions f to some defined on M to some new functions g that are defined now on n, and g is defined simply as composition between f and t. So conveniently, we write this t sub f is basically the functional transformation associated with the map t. And of course, once you have a single map t, you can transfer any kind of function, right? So there are no constraints on the kinds of functions you can transfer. So this could be like some localized functions on some region, or basically any function you can transfer. And this functional mapping t sub f has certain properties that the original mapping t doesn't have. So the first property is that it's linear. So it's linear in the sense that if I have a linear combination, so if I have some scalar coefficients alpha 1 and alpha 2 and two functions f1 and f2, if I take a linear combination of these two functions, the image of this functional transformation is the linear combination of the images. And this is just basically a direct property of functional compositions. I mean, it's not really a theorem, it's just basically by definition it's true. The other thing is that it's complete, and when we say it's complete, we mean the following. Suppose that I know that this t sub f came from some from some point-to-point map, but I don't know what it is, right? So I have some oracle that for every function on the source shape produces a function on the target shape, and I would like to recover the original mapping t from this oracle. And it is possible to do that, and there are many different ways, but the simplest probably is you can think of, you can create highly peaked functions like delta functions on shape M, and just look at the image of these delta functions on n, and then this gives you basically the underlying correspondence t, right? So we can recover the pointwise correspondence t from this functional transformation t sub f. So this is the property that we call it complete. Now, so this is kind of very straightforward. There's now an extra thing that we are going to use, and we basically make this assumption that both f and g lie in a sufficiently nice space of functions. And what we mean by sufficiently nice is basically, for us, we mean that they're both square integrable functions. So this is what I mean by L2 here. So f and g are both square integrable functions. And if this is the case, then we can express both f and g as a linear combination of some basis functions. So as probably some of you know, the space of square integrable functions can be endowed with a basis. So you can construct a set of basis functions phi such that any function f that is square integrable can be written as a linear combination of these basis functions. And the same is true for the image of f, this g. Right? So there are some scalar coefficients b such that b sub j, such that if I take the linear combination of the basis functions phi j on n with these scalar coefficients, I get back g, right? And if g is a square integrable function, this should always be possible. And now we kind of make this small observation, which is that now we have a linear transformation. So this t sub f is a linear map between basically two spaces. So it maps basically f to g. So what that means is that it must map these coefficients ai to the coefficients bj, right? This is just, the property of this t sub f. And we know this is a linear transformation just by the definition of pullback. So what this implies is basically there's a linear transformation between the sets of coefficients ai and bj, and this linear transformation is exactly what we'll call a functional map. Okay, so, I mean, this sounds maybe very straightforward, but actually this turned out to be extremely useful over the years, and I'll show a few different applications of this very basic idea. Now, there's a question of what kind of bases. So I said, we assume